In this video, we introduce optical flow training under limited label budget via active learning for ECCV 2022. Optical flow estimation is crucial for pixel-level video motion analysis. Optical flow is defined as the 2D displacement vector pointing from one pixel to its corresponding position in the next frame. Its estimation is a dense correspondence matching problem. Most existing methods are either supervised or unsupervised. Supervised methods have better accuracy. However, optical flow labeling can be especially difficult and expensive. Therefore, many unsupervised methods have been proposed based on the brightness constancy assumption, which require no labels but compensate accuracy in return. In contrast, we studied the semi-supervised setting, where only partial labeling is available, to better balance accuracy and annotation cost. Note that the percentage of labeling is variable depending on the budget we have. The label budget is a very common constraint in real practice, so it is important to study how to optimize accuracy under a usually limited label budget. Now, given a label budget, for example, we can afford 20% of the data to get labeled. A common question is, which 20% of the data do we label? A naive answer is random selection, but it is possible to do better. Active learning allows the trained model to pick valuable samples that may help the most to query labels. To the best of our knowledge, we are the first to study active learning as an approach to tackle the high annotation cost of optical flow training. Now we introduce our active learning framework. The original unlabeled data is split to two sets, D1 and D2. We first train an unsupervised model M1 on dataset D1. This model should work decently. Then, we use this model to predict optical flow on dataset D2. For each sample prediction, we evaluate an uncertainty score based on heuristics, which we will discuss later. The samples with top uncertainty scores will be selected and sent to an expert annotator to query labels. Hopefully, labeling these samples will help the most in improving our optical flow model. This process produces a partially labeled dataset D2. Finally, we fine-tune model M1 on this newly labeled D2 to get our final model M2 using semi-supervised training. Specifically, we adopt the state-of-the-art unsupervised AR flow as our network, and we use the same loss for unsupervised training. In semi-supervised training, we make supervised and unsupervised losses, where the supervised loss is from PWCnet due to its similar network structure. For uncertainty scores, we test three different definitions. Photometric loss indicates poor photometric matching. Occlusion ratio indicates more occlusion problems and poor forward-backward flow consistency. Flow gradient norm indicates non-smooth flow and motion boundaries. All these three are indicators of poor flow estimation by heuristics, and we test each of them separately. Now, we show our results. We first show our baseline semi-supervised training results with random selection of labeled samples. For 4 different datasets, the arrow label ratio curves visualize the accuracy annotation cost trade-off. We can see even adding a few labels helps reduce the error significantly. Active learning results on the validation set show that all uncertainty scores work well compared to the random baseline. Specifically, the occlusion ratio score works consistently better than random, so we choose occlusion ratio as our final uncertainty score definition. Benchmark tests also show similar results. Our active learning method based on occlusion ratio works consistently better than the random baseline for all tested label ratios. Notably, our method can achieve errors close to PWC, a supervised method with similar network structure, even if we only use 20% of the labels. Through visualizations, we also found that the most challenging samples with large errors are selected by the model to query labels. This in some way explains the success of active learning. For more details, please refer to our paper. You can also scan these QR codes to access our paper and code. Thank you for your time.